What's good, you guys? I hope you're doing well. And in this video, we're going to continue our stacks class. More specifically, we're going to cover our methods that we're going to have for this class. Mainly our method to add data, which we'll call push, our method to remove data, which we'll call pop, a method to print everything in our data, and a method to check if it's empty or not. And lastly, we'll have a simple method to search our data structure to see if there's a value in it or not. So why don't we get started? We left off by creating our constructors, our destructor, and two getters for the class. So now I will be implementing the push, which will take some s value, and what we'll do is that we'll see if our data is equal to null, meaning that our stack is empty. And actually, why don't I just say that? Why don't I just say if empty? If empty. And actually, I'm going to make this change up here. If s empty. If it's empty, we'll make sure our stuff is empty. And then we'll go down here. So if it is empty, we're going to say now that data is going to get a value. So we're going to dynamically allocate one value for it, which will be new s. And we'll initialize it with our argument value. We'll have our size equal to 1. And that keeps it simple. And I like simple. But unfortunately, we need to take a look at the non-simple case. When it's not simple, I gotta take a copy of our size. And then I'm going to make a copy of it. So I'm going to say data copy is equal to new s. And then we're going to have the size of our data size. And why am I taking a copy of the size? Well, what I'm going to do is that I'm going to have my current data be held in data copy, and then I'm going to delete my internal data because I need to resize my array. I need to reallocate it. And this is going to be the process in which I reallocate data for my array. Then I'll have my size t of I, which will be my simple iterator. And actually, I'm going to go up here and change that. I don't want to use auto. I'm actually going to use size t of I, and I'll declare that above here. Just because I don't want to use auto, I want to make sure I is the same data type as s size, so that way the compiler doesn't complain. But anyways, I'll begin with my for loop with my conditions here, and then I'll start copying our data to our data copy. Once that's done, we are ready to deallocate our data. Then we will reallocate our data so that way it's data size plus 1. And now we can make room for the value that we're going to push. So then what I'm going to do is that I'm going to have my loop again, and I'm going to iterate through my entire loop just again. But now it's going to be, data plus I is going to be equal to data copy. So I essentially copy everything back. Then lastly, I'm going to say data plus I is equal to value. So why am I doing that here? It's a little bit tricky, but one thing that I'm doing is that I'm kind of like exploiting the way a for loop works, because I is still going to be incrementing. I continues to increment, and we break out of the for loop when I is equal to data size. But now, because our data has a capability of data size plus 1, when I have data plus the data size, I can add our new value to it. The last index that we can access safely is going to be data size. And when we break out of this for loop, we break out of it because I is equal to data size. So this is nice because this lets me add my value to data at the end of data without any problems. And this will lead me to properly add or push my value to my stack, and then I'll have to increase my size by 1. And then at this point, I'm done with my data copy, so I'm going to delete my data copy. And this is the complicated part for adding to the stack when I push to it. And again, to kind of give an overview, if it is empty, that means I can only dynamically allocate one value. So I do that here, and the size is equal to 1. If it's not empty, what I'm going to do is that I'm going to take a copy of my current data and store it in data copy. I'm going to delete my data and reallocate a new size. Well, its previous size plus 1. I copy everything back, and now I copy the new value that I'm pushing to the stack. I increase my size by 1, and I delete my temporary copy. Doesn't seem too bad, huh? Well, now let's take a look at deleting data, which we'll call pop. So pop will take no arguments because we're going to be deleting data. If it is empty, we can like throw an error, but for this case I'm going to print out something, and since I'm printing out, I'm going to need IOStream. And I'm going to say stack is empty with a new line, and that'll be it. And then after that I'm going to return because I don't want to do anything. So other than that, what we're going to do now is we're going to check if the size is equal to 1. Because if it is, what we're going to do is that we're going to set size equal to 0, and we're essentially popping one thing, or I guess popping one value off the stack, and we're going to make it empty. So I'm going to say delete data and then data equal to null pointer, just to be sure. I want to make sure that we deallocate the data that's there, and then we set it equal to null pointer. Otherwise, if there's 2 or more values, we're going to take a somewhat similar approach to how we push data the complicated way, where we need to take a copy of everything, reallocate, copy it back, and remove stuff. So here's how I'll do it. So first I'll have my size t, which will be my data size. Quite similar, huh? So we'll take the size of our current data, and then what I'm going to do is that I'm going to have s, and I'm going to have my data copy, and we're going to dynamically reserve. But instead of doing data copy, I'm actually going to do data copy minus 1. Or sorry, data size minus 1, right? Because we are deleting a value from our stack. And when we push to the stack, we add our new value to the beginning of our dynamically allocated array. So it makes sense when we're pushing off the stack that we delete our data from the end of the array, because that's where we add our data. And again, with stacks, the end of the array in which we add our data is the end of the array where we must remove our data. If I really wanted to, and if I really wanted to challenge myself, the way I could add data to my array could be in the front of the array. That would make things a little bit more complicated, and I think it'd be unnecessarily complicated, so I'm not going to do that. Now I'm going to copy everything to my copy of the data, and here we are. We have our data copy plus I is equal to our data. And notice how the ending condition for this for loop is going to be data size minus 1. We're going to be excluding the data item that we want to pop. And actually, in this for loop is where we do the popping of the data itself, the exclusion of copying that last data member. Then I'm going to delete my array, my dynamically allocated array, and then I'm going to reallocate it with data size minus 1, so that way it has one less capacity of data than it did before, because again, the purpose of this method is to remove a data from our stack. And here's how I do it. I allocate a memory for the data size minus 1 because I am removing one data member from my dynamically allocated array. And then here what I do is that I copy everything back to where it was. So I have my data plus I is equal to data copy plus I. Keeps things nice. Now what's left is that I'm going to decrement my size, and I'm going to delete my copy of my data. And this concludes how we pop our data. If, let's say for example, I wanted to implement my stack using a linked list, for example, a doubly linked list, here I would just delete from the back, and if I were to emulate the push method using a linked list, I would say add back, right? So we have add back for push and remove back for pop. So just in case you're out there and you're implementing, if you're doing the logical thing and you're implementing a stack using a linked list. That's the way I do it. Next, we're going to print our data for our stack. So we'll have our size ti equals 0, I is less than size I plus plus. And what we want to do is we want to print out everything just as is, and it'll be similar to how we go about printing a array that's been allocated through dynamic memory allocation, where we have our offset where we want to dereference, and then after that we'll be good and we'll add our new line, and that'll be it for the print. So then we have our empty method. I don't want to have a void empty method. I want my empty method to return something. I'm gonna make this const. We can actually, let's make our print const, because we're not doing any manipulations of data there, we're just accessing it. So we're going to return is that we are going to return size double equals to 0 and our data is equal to null pointer. And that's why up here when we deleted our data and it becomes 0, that's why I set size equals to 0 and data equal to null pointer. So that way when I check if it's empty, I know for sure that, hey, you know, when I make it empty, it's going to reflect that it's empty, because when I decrease it from 1 value to 0 values, I set size equal to 0 explicitly and data equal to null pointer explicitly. And next I'm going to have my search method, and this is actually going to be an implementation of linear search for my stack data structure. And again, because with our stack we can add and manipulate data in any order and it can seem random. Just because you as a user or anyone else that uses the stack, they can add data to the stack in whatever order, its contents can be in whatever order. So then I check, so if you need a value here, so s value. So if our value is equal to data plus I, so here that's where we'll be searching it, we're going to return true. Otherwise, as we keep looping and it's not found, we're going to be returning false. So the search that we use for our stack data structure needs to be a linear search, and again, to kind of beat it into your heads, this is because we can add data in any order to our stack, so we can't really make any assumptions when it comes to searching it. And since the inner workings of our stack is an array, well, we use the linear search as if it was an array. But anyways, this is going to wrap it up for these methods. All the methods that we're going to be implementing for the stack. In the next video, I'm going to go about operator overloading, and I'll be overloading the equals operator. I will also be overloading the double angle brackets operator for printing with std cout. And I'll be overloading the double equals operator as well as the not equals operator. And after that, we'll test our stack class to make sure that it works. I'll see you in the next video.